of HPC systems from Pnnl, where I'm at now, and also from Los Alamos in the past. And it's interesting to see the development of these systems in a similar way to Dan was saying yesterday about looking at trying to achieve a gigaflop performance for $50,000. Wow, gosh. Sort of dates you and sort of makes you realize that the people with very little hair in the room have gone through a lot of pain in previous generations of systems. Pnnl is in the middle of the desert in Washington State, a very dry place, 8 inches of rain a year. And that's a picture of our campus. It's right next to this giant Columbia River that we stick straws into the ground and suck out the water to make it green. The Columbia River, in actual fact, is pertinent to some of the talk here, in that it provides a vast amount of electricity, hydroelectric electricity, and building a facility right next to a hydro dam would actually entail us to achieve an energy budget of 2 cents kilowatt hour, which is very impressive compared to the industry standard, or the country standard, I guess, of 11.5. Factor of 5 cheaper electricity that we can tap into should we want. I'm going to start off this talk very light. I'm going to give some experiences that we've had at Pnnl, both from applications, systems, and some of the research that we're heavily involved in. And my training at Los Alamos for 10 years taught me that I should always draw graphs like this. Things get better over time, right? They improve. And if we look at the advent of performance, well, yeah, things have got better. I see some people in the room that were involved in ASCII Q, in actual fact, 20 teraflops. The fastest machine on the planet, not the Japanese beat us to it, the Earth simulator. Petaflop. The first petaflop machine was actually at Los Alamos, heavily involved in that in 2008 in its deployment. And of course now we're looking towards exaflop computing, and the exascale initiative in the Department of Energy is pushing forward already various aspects of technology as well as software. What comes after exaflops? Go on. What? What? I think it's Zeta and then the other. Yeah, but actual fact, it's not either of those two. You know, we're already in this regime that performance doesn't really matter, right? We're sort of ending up in the situation where we know things are increasing, right? Performance will increase, we hope. Concurrency is certainly increasing, but also faults in the system are increasing, in part due to the scale, in part due to the pushing of the technology. And of course, the power is also increasing, the power cost. And so, you know, we're seeing this shift from performance into looking at maybe looking at allocations in terms of a power budget, megawatt years instead of million CPU hours, and also maybe we should be considering more in terms of data movement operations that we're retrieving per second, rather than gigaflops per second. Data movement is the key. The processing of the data is the key. HPC at Pnnl. Well, we're a member of what is called the Exascale 7 group of labs, including Oak Ridge, Argonne, NERSC, Berkeley, Sandia, Los Alamos, and I missed one, I guess, but it's probably not important. Livermore, okay, yeah, I've heard of Livermore as well. Inside the E7, we're actually assisting DOE, the Advanced Strategic Computing part of it, and looking at various programs in advancing technology development at the node level, processor and memory, and also in terms of networked technology as well. They've got several programs in flight at the moment, fast forward they call it, and design forward, trying to push the envelope on the technology to get as towards exascale as soon as possible. We're also at Pnnl a lead of one of the, shall I call it a focus area, a research area on performance execution. And that is a central activity that cross-cuts many other activities for the exascale initiative. Pnnl has actually had a long tradition of being involved in HPC. We're very well known for some of our programming models work, some of our application work. We developed a programming model called global arrays, predates MPI in actual fact, and it's widely used in some of the applications that we've got. And I'll say a little bit more about that. We're very heavy users of MPI and MVAPICH too. And we also look towards highly energy efficient solutions, both from the embedded and supercomputing regimes. Very much a collaborative research environment we've got, open research. We're an Office of Science lab, and we partner an awful lot. And we take on many visiting researchers and interns. And I was talking to somebody yesterday who jokingly said, well, you haven't been here for 7 years, but I've only been back from Pnnl for 7 days since the end of his intern. We work with the DOE a lot, but also DOD and various agencies inside the DOD, as well as DARPA. Some of our primary research in HPC are to do with modeling and simulation. I'm an application-centric modeler, in actual fact. I like to know what applications we'll be able to achieve on future systems. So there's a lot of modeling and simulation that goes on there. That's my expertise. Programming models, I refer to global arrays, and also looking at dynamic runtime systems, how they may be able to be used to overcome many of the issues going forward in terms of faults, in terms of managing power constraints as well. And also putting in place many advanced test beds. This is a sort of graphic cartoon that illustrates sort of where we need to be at in terms of looking at future systems. Many people use the phrase co-design inside the lab community. We've got co-design centers that are looking at the design of various new applications for use in the exascale era. Those applications need to think about many different aspects, much more than performance. Like I said before, performance, power, and reliability are all equally important. There are factors that go into that. Algorithmic factors, the applications, the instantiation of the algorithms, the programming models that get used, runtime systems, how it handles the dynamic behavior, and of course the underlying technology. All of those things make up the system. And in terms of co-design, what we're seeing is a various combination or consideration of those factors, but none have really gone the full 9 yards and actually looked at all of those in the same breath. We need a much more holistic view to what's going on here. This is what I call my instrument, my banjo, in actual fact, my 5-stringed instruments. And we've seen experiences of playing this instrument in many different ways. Porting applications onto the architecture, the directed arrow is meaningful there. Everybody ports applications to a new architecture, right? That's not co-design in actual fact. Neither is this. Designing an architecture to a set of applications. And in actual fact, we saw that through personal experience within what was called the DARPA HPCS program that ultimately contributed to the production system Cascade from Cray and also the Power 7IH from IBM. In fact, we were very much involved in the guiding of the design of the Power 7IH that ended up in a 2-level fully connected network, very similar to the Dragonfly that Cray used. What was interesting, in actual fact, was when we started to see the need for changing the programming model and the runtime system in conjunction with the application. We did that, in actual fact, on Roadrunner, which was the first petascale system back in 2008, and it was an accelerated system. In actual fact, back in 2005, when we started analyzing such a system, we didn't use the phrasing accelerator. That was alien to us. We used the phrase a two-level heterogeneous system. Two levels because we had the main processor and we had a co-processor using a different ISA, heterogeneous. Okay, such a system now is all over the place. We heard various references and talks about the Intel Phi systems, NVIDIA. The interesting thing in that particular co-design experiment was the fact that we had an 8-core accelerator. It was a IBM Cell processor from the PlayStation 3, a modification of that. And we had a host, an AMD dual-core Optron. And rather than shipping down work onto the accelerator, using MPI on the host processor and shipping down work onto the accelerator, we developed what was called a reverse acceleration model, in which we assigned an MPI rank to each of the co-processor cores, to each of the cell cores. They became first-class citizens, and we offloaded things that the accelerator was not capable of doing to the main processor. A reversal of sort of view of what an accelerator was, and that proved extremely popular for some of the applications. And even now we're seeing on the Intel Phi having MPI per core as well, as long as you've got the memory space. In actual fact, back on the Cell broadband engine, we did a lot of work to optimize memory use, and only had a subset of the MPI implemented on each of those cores. We also have looked at co-design for energy efficiency. That is a coupling between the application and the runtime system. There's a lot of work that goes on in terms of designing runtime systems that respond to the activities that are going on around it. That's its job, I guess, in a lot of ways. But by coupling extra information provided by the application, we can actually make significant extra savings, preemptive savings. Knowing what's about to happen and how long for actually enables us to improve the energy efficiency. We've also seen co-design for fault tolerance, in which we've supplemented our programming model with fault-tolerant constructs. And I'll say a little bit more about that, but it's impacted the application and also the runtime system. We're very fortunate at Pnnl in having control over the global arrays programming model, and so we're free to extend it as such if and when the application needs arise. And the fault tolerance there, I'll say a little bit more, but that was put into production use a couple of years ago. MVAPICH at Pnnl. I went around and asked various people, various users, various system people and application optimizers what their view of MVAPICH was. And it's sort of a dangerous question to ask. And I'm going to just say what they said unabridged. And it was a ratio of 2-to-1 MVAPICH use to any other MPI library. It was the best performing library and MPI of choice, which is very good for me to stand here and say that. All the way back, I remember in the early days of putting in place accelerated systems, MVAPICH was always the one that was reliable and easier to use than anything else that we had available to us. Of course, many of the users I also talked to at Pnnl, they said MVAPICH what? Which is also very good because they were using it just out of consistency, and it works. You know, why should they worry about it? And that's a very strong statement, I think, in the excellent work that is going on at OSU. What I'm going to touch upon are really some of the systems that we've got in place at Pnnl, some of the applications, and also some of the research. Much of our research is certainly directed into putting into practice, not developing techniques for the sake of it, but developing techniques that are put into practice, many of which are put in the context of our global arrays programming model, but could equally well find use within the MPI space as well. One of our major machines is in place within an umbrella called institutional computing. This is about 80% internally funded to try and promote HPC activities across the board within the lab. We're a very diverse lab and got many different application areas. And putting in place a reasonably sized system that people can start to use and to scale up their applications has been very advantageous and pushing forward many different application areas that traditionally have not used HPC. The main cluster contains 660 nodes. It's got quite a bit of memory per node, 64 gigabytes per node, InfiniBand network, and the whole design of the system was to allow individual projects to buy into it, actually to buy onesies and twosies or tens of nodes to add to the system and to take advantage then of the full scale of the system when they needed it. It's quite an interesting model of how that worked. It's got a very large file system, and in actual fact, when you talk to the institutional computing guys, the file system is the center to everything that is going on here. The data is central. And of that data, we've got various different computing systems. The largest one I just described. We've got a number of additional small-scale production systems on that. Hadoop cluster, an Intel Phi testbed, a GPU-based system, also a Windows HPC box. It's currently being upgraded to Haswell and FDR, which is going to be in place within the next few weeks. What's important about this also is to give people a stepping stone from their experiences here into the larger systems, the LCFs, within the DOE community. The LCFs being at Argonne and Oak Ridge, as well as the machine at NERSC. Another machine that we've got, a more capability-based machine, we call it Cascade, nothing to do with Cray. It's a 3.4 petaflop system, 1,400 compute nodes, built around Intel Phi. And it's interesting coming along here for these 2 days and seeing so many talks actually from Intel. It's also interesting hearing from some of the work that Alex did to see that you can get speedups from the Intel Phi, a factor of 2. And in fact, I'm going to show you something that we've achieved for some of the applications in excess of that substantially. One of the factors inside this machine, again, is the amount of memory that we put into each node. This machine has got 8 gigabytes per Xeon core, and it allows us to handle larger problems than many machines in an equally sized sort of node count. We're expecting to deploy a second component of the system later next year, and certainly on this system, we're working with OSU to put in place MVAPICH to Mike version and make that accessible to all the users. I should also give credit that this machine is actually part of the DOE Biological and Environmental Research Department. And we've got a lab within a lab, in actual fact, at Pnnl, and that's contained as a user facility, a user instrument, as they call it, within the environmental and molecular sciences. And as a third part of the component of the systems that we've got and put in place, we've got a number of advanced test beds. And these are really starting to be put in place for different clients that we've got, different people that we work for and work with, and state-of-the-art computational resources that are tending to be very highly energy efficient. And we put that in place initially as part of what we call the embedded HPC lab, and it will become the energy efficient HPC lab with very little change. But a number of programs that we support in that lab. There's a program called DARPA Perfect, which stands for the Power Efficient Revolution for Embedded Computing Technologies. And its goal is to achieve 75 gigaflops per watt on certain applications by the end of the program for embedded computing systems that could be deployed in UAVs, unmanned aerial vehicles. And this is 2 years into the program now. I've got another 5 years to go. And we're actually supporting that through a diverse number of different systems that are accessible across 16 teams across the country inside that program. We also support another program called SEEK, putting forward a suite of applications and kernels for embedded computing. And this may well be similar to the top 500, but for embedded computing systems, and very much focused on energy efficiency, not performance. We're looking at putting in place also a DOE test evaluation and design center that is focused solely on some of the larger scientific applications, but looking at state-of-the-art machines and technologies, putting in place test beds that could well be deployed in future systems. Part of our strengths is actually in the modeling and simulation, and knowing at the small scale what applications can achieve can be used as input to many of our modeling and simulation capabilities to look at what large-scale systems could achieve should they be deployed. Also help in their design as well. Some examples of the application base. We're known for computational chemistry, NWChem, and I don't know if Jeff is here or not. Yeah, it's the next talk, right?
Yes, sir.
Yeah, so I don't see him, but
he has some problem, so
oh, okay.
He will talk remotely.
So I was going to talk remotely, so I can say what I want while he's not in the room. But Jeff was a postdoc at Pnnl. But NWChem is a major framework for computational chemistry. It absorbs a lot of the cycles on the leadership class machines, and it is certainly led by Pnnl. It's Pnnl's marquee application, if you want, and it's also built around this global arrays programming model. I'll say a little bit more in a minute. Subsurface modeling as well is a very important activity to us, looking at the dispersion of materials in the ground, looking at the chemical reactions that might go on in a number of different ways, and the diagram there just shows the sort of different scales from coarse to fine that some of the applications actually look at. Climate and atmospheric modeling in particular is something we get involved with. The community efforts, the community atmosphere model, and also the Weather Research Forecasting Code, WRF, we're a major contributor to. And also, interestingly, looking at some of the physics side of things, high energy physics. The one here I've called upon is something known as Bell 2, and trying to examine why the universe does not contain antimatter. There's an accelerator been put in place at Tsukuba in Japan at the cost of 400 million by the Japanese government. It produces data at the rate of 1.8 gigabytes per second. It's actually being shipped across to Pnnl. And a lot of processing that is available across the country, but a lot of processing on that is taking place. That is not traditional scientific computing, but much more as what I consider as a workflow type operation, in that there's jobs are small, processing parts of that data that's coming in, but there are many jobs to be processed, and the distribution of those jobs is the challenge that becomes a wide area problem, not just a single machine problem. Global arrays I referred to a little bit, and I'm not going to go into any detail on this apart from to say that a single array, the idea inside global arrays is that a single array can be accessed, data from that array can be accessed anywhere in the system through a single call. You don't need to do a send or receive and know where the data is. The system will actually map a large array across the system, and all you need to do from the programming side of things is to say, I want to get this data from this array, from this index to that index. And that data might well be mapped across many processes, but a single call will get that data into a destination that you want. Put-get type activity. And that's very advantageous for some of the computational chemistry, in which you get very large arrays that you cannot replicate on each node, but you need almost random access to those arrays over time. Knowing the interactions, say, between two types of atoms and accessing data that represent those atoms that could reside anywhere across the system. As I say, that model actually predates MPI, and it's very much interoperable with MPI and MVAPICH, and in fact it relies on the MPI process management to work as well. And we're looking at the use of MPI 3 in exactly the same way as Jeff's going to be talking about, and using the put-get activities in that. The diagram here actually shows the extent of its use on Python. Actually, it's scheduled in 2012. Just a snapshot of what was published by Oak Ridge and the use of the different applications. NWChem used a significant amount of processing cycles on that system. And it does the different LCFs at Argonne and at NERSC too. So it's a very important application. I could go into a lot of details about NWChem, and I could talk to this slide, and to be honest, I don't understand much about computational chemistry at all, apart from I know it involves interaction of molecules. And NWChem, as I say, is a huge framework that has got a big user base installed at about 3,000 sites across the country. And it's in very active development at Pnnl. It's also open source as well, so very much available for people to use. This is part of the recent results that we got from NWChem, and this can be talked about at supercomputing. What's interesting is this chart here, and this is for our Cascade system, the Intel Phi based system, and it shows the performance when using only the host CO, when using the Intel Phi, and when using both of the two processors in tandem. The coupled cluster method here is actually consists of many tasks that need to be processed. The interactions between two types of molecules over and over again, different molecules. What we see in actual fact is that we see a significant performance improvement when going from just using the Xeon down to using the Intel Phi, a little bit more than the factor of 2. We're seeing maybe 2.5, 3. But also in this model, we're able to take advantage of both processors within the system, both the host and the accelerator, which is significant. Another example from the computational chemistry domain is classical molecular dynamics. And inside molecular dynamics, you look at the interaction between atoms within a certain cutoff distance. In 2D, consider the central sort of square here. It takes in the interactions, or calculates the interactions between all atoms within the central point and the cutoff radius that may reside on neighboring processes. And because of symmetry, it gets a little bit simpler in terms of the number of interactions you want to do. But in order to increase concurrency, the application we got, Argus, increases concurrency by an order of magnitude by actually looking and parallelizing over interaction pairs. So considering the interaction between what's inside this guy and what's inside this guy, that is a unit of operation that can also be further subdivided into multiple tasks too. The general approach actually we're taking in many of the applications is to try and make them more task-based, to increase the or to express the concurrency that is available to us, and also to make them, wherever possible, asynchronous. And that's going to be increasingly important as we go forward. And this is actually is a sort of segue into some of the more researchy bits that we get involved in. Energy optimization. We had a development of a technique that we call energy templates, and that is building in information about when processes may be idle during the course of their execution. In terms of the interactions that I just described for the molecular dynamics, we end up with a natural load imbalance in terms of work across processor cores, if you want, as shown by this diagram here, time left to right, and processing activity shown by the black arrows, and the green shown by periods of idleness. In actual fact, what the application does in order to express the amount of concurrency is it leaves significant load imbalance on the table. And of course, in terms of looking at it in the energy efficient point of view, all you can do is very simply drop down cores with very little work to do, dilate the amount of time it takes, and hopefully finish at the synchronization point, which is shown as synchronization point in this diagram, but is not in reality. But at dilation, at a lower P state, for the processes will save energy. The important part of this, in actual fact, is providing the application information down to the runtime, separating out the mechanisms used to save the power, save the energy, from the application. Don't build in to the application the mechanisms for saving the energy, but express the information that's needed by the runtime system to save the energy. Only in fact, we have done that for various applications, some in the global arrays domain, some in the MPI domain, using PMPI of all things to build in little micro models about when significant periods of idleness are expected in the application, and then allow the runtime system to take advantage of that knowledge, either to clock down, to change the voltage frequency, etc. And also, in some cases, to idle the cores and then wake them back up on message arrival, event-driven. Another activity, in actual fact, in the energy space is work that was done by a number of my colleagues in looking at the cost of data movement. A lot of people have given lip service to the fact that significant energy cost is inside data movement. And it really has been lip service. Because when you look at the literature about people quantifying how much cost is in moving data between levels of the cache across the system, as such. There's been very little analysis on the application side, if any. We published some of this work back in September 2003, where we carefully designed a set of benchmarks, micro benchmarks, for determining the energy cost of data movement in this case, an AMD Intel processor, but looking at how much going from different levels of cache and across the systems, and forming a basis of a model which looks quite simplistic. The detail of the work was actually in the design of the micro benchmarks to separate out the true cost of the data movement. And then applying that to a number of applications. Neckbone is an application coming from a co-design center from Argonne. And looking at really where the energy cost is. And just as an example there, moving data from L1 to the processor registers is the dominant in this particular application. But there are other factors that come into this. And in actual fact, in the systems at the moment, less than 50% of the energy cost is currently in data movement. The balance there is expected to change down the road, but at the moment is not a significant cost. Another approach from the power side that we're taking is a little different in that, and called power steering. And what we're doing here is that we're trying to direct the system power to where the work is. We've done a lot of work in the past as a community in load balancing, in equalizing the work across the system so that things can move in almost lockstep across the system. Of course, that data movement costs cycles, costs energy, and sometimes the complexity of the load balancing outweighs the benefits. In some cases, that's a bad thing, of course. What we took here is an exploration of leaving data in place, leaving the work in place across the system, even if it becomes imbalanced. Maybe through particles drifting, through AMR type activities as well, but leaving a natural load imbalance of the work, and then assuming that we can apply a higher P state to where that work is. We mimic that on a real production system by allowing the system to run at a mid P state as a baseline, and then allowing cores with more work to run at a higher P state, higher clock frequency, if you will, and those cores with less work to run at a lower P state. And that diagram just shows for a number of parameters to do with the computation ratio and the load imbalance, that you can actually get significant runtime improvements and energy savings by leaving the work in place and allowing those activities, the change of the P state, to match the amount of work and allow really for looking at systems that are power constrained, not running them all at the high level, but allowing that variation in P state to take place. Again, some of this comes from knowledge about what is going on in the application, and allowing that knowledge to be used within the runtime system, in this case, again, to vary the P state. In terms of fault tolerance, we've got some work in flight looking at hard faults and soft faults as well. In terms of some of the work that we did on fault tolerance, we designed a system that allowed critical data to be replicated across the system. If you consider this cartoon here with the 4 partitions of this data, those 4 partitions are mapped across the system in a primary distribution and also in a secondary distribution. There's a replication of that data, 2 replicants in this case. What this allows us to do is consider one of these nodes failing, right? If this node fails, the primary copy of this blue block is still accessible, but from a different node. So we designed a system, an extension in this case to global arrays that allows us to specify what was critical data, what data needed to undergo this replication. And also, on a node failure, what should be done to recover the tasks that were in flight on this failed node and recompute those tasks. Very much a task-based operation, taking out the synchronous nature of what is going on in the applications, which is possible for many applications, and then allowing the recomputation of those tasks. That highly successful, and as I say, is in production and was demonstrated in quite a big way on Titan. But it allows the job to continue in the presence of node failures. Significant as we scale in size. Oh, we did also some analysis of soft errors by bit flipping various bits within the data structures that we're dealing with in applications, looking at the impact of which bit from 0 to 63, I guess, which bit got flipped, and the impact on the application, whether or not it continued, whether or not it continued but required more iterations for convergence, whether or not the convergence did not happen, whether or not the system crashed. And in actual fact, we did some work in analyzing too what would happen if we could do some detection mechanism for when errors did occur and also correct those as we went along, which actually reduced the number of failures significantly. Let me say a little bit more as we go into the technology a little bit more. I'm going to say a little bit more about this DARPA program because we are seeing a convergence of activities in technology space from the embedded space into the supercomputing space. We talked about ARM64. Gillard mentioned ARM64 yesterday. Very important technology we see going forward. But there are various other things going on in the DARPA space that range from actual device technology developments, pushing forward down to the 5 nanometer regime, and also getting towards what is called near threshold voltage, near threshold operation, in which case things naturally become unreliable. And if we go too far down that space, then things will become too reliable, but we've got to handle pushing down the energy envelope. Some of the architectural issues that are going on in in this program to do with processor core design, memory design, and also some of the software issues. In fact, the whole program, it's a large program, has got those activities labeled on that diagram, which is fairly legible. But just to show you the extent of what is going on inside this program, we're actually at Pnnl, what is called a test and validation activity that is really verifying what is going on in each one of the performer teams. And we do that by supplying state-of-the-art resources, by also supplying software, benchmark suites, and also looking at modeling and simulation to back up and agree with or disagree with many of the results that are coming out of the performer teams. Just an example of some of the baseline architectures that we put in place, Kayla, the NVIDIA ARM combination, IBM Power 7, Encore, which is an interesting combination of ARM and DSP chips, control as well. And part of this also is looking at how we do power instrumentation as well, looking from wall power down to socket power and beyond. As part of the test infrastructure we've also got in place HMC, HMC is a hybrid memory cube from Micron, and is a very interesting memory technology. Many, I'm sure, are aware of. And at the moment, this is up to generation 2 device, and it's got no host at the moment. It's been driven by FPGAs that can be used to examine individual characteristics of this device, individual access patterns, if you want. And we're using that information actually to drive input to many of our modeling and simulation activities to look at what this device is achievable when it is deployed in a system. And also, interestingly enough, how this device may well evolve over time. The HMC is a stack of memory chips, but it's also got the ability of doing some processing, what they call a logic layer in there. And it's a natural extension to gradually increase the amount of processing that this chip stack is capable of doing. Perhaps, for instance, putting PIMs on there, perhaps putting ARM cores in there, perhaps doing a lot more processing inside the memory than we're used to, and doing it memory side rather than processor side. It poses sort of interesting questions about how such systems may well be programmed in the future, whether or not we need to do it explicitly or whether or not we need to rely on tools, compilers, and such to deal with some of these issues. Another system in terms of test beds that we've got is a system called Seafoam. The name is meaningless in actual fact. What is interesting about this system, a system that we're putting in place in the next 2 weeks in actual fact, is that it's got a reasonable fidelity on the power instrumentation, using a specific device from Penguin Computing that operates at a kilohertz, and that has got 21 channels of power measurement, and that resides in each node inside this cluster, and this cluster's got about 64 nodes inside it, consisting of Intel processors as well as AMD Fusion APUs. Another important aspect of this, in actual fact, is not just the power measurement capabilities. We're also starting to instrument for thermal temperature as well. 21 channels, 8 of which are dedicated to temperature measurements, and that's done on each node. It's interesting extending that to thermal activities, thermal properties, and looking at large-scale system aspects to that as well, as quite often overlooked, but thermal temperatures can impact the processing significantly through the management of temperature by the system, as well as knowing, in part, how much performance is being left on the table. And I could say a lot more about that. Further test beds we're putting in place. Again, Gillard referred to the Power 8 and NVIDIA combination and the Open Power Consortium. We're putting in place a test bed on that in the near future, an ARM64 I mentioned. And what is also very important is to use these test beds not only for application readiness, but also for system software readiness too, and we'd be very happy to work with the OSU team in looking at many of these test beds, making them accessible as well. Our own interests, research interest, is directly related to how large-scale systems could look using and being built from these individual components that we're seeing in the technology space. Further work on our modeling side actually includes looking from a modeling and simulation point of view, a predictive point of view, at possible future technologies. I'm very curious what Mellanox are doing with their silicon photonics. We're actually involved in a DARPA study right at the moment that is looking at the impact or the possible impact of silicon photonics over the next 5 years that may well lead to a new DARPA program 6 months down the road. And we're also looking at using modeling and simulation on extreme scale scientific workflows, some of which I did briefly mention earlier on. What we see at a high level is that, and it bodes well for my own background, is that we're seeing models being used in different aspects of the system operation. Performance models, maybe power models, maybe even reliability models that can be used by the runtime systems, for instance, to guide their operation. Maybe inside compiler technology as well, and to help in the programmability of these future systems too. Performance models can be used to inform what is about to happen before it does happen, to allow systems to be more proactive than reactive than they have been in the past. After all, many of the systems down the road are going to exhibit much more dynamic behavior than we used to. I'm going to summarize what I've got here in my talk, and coming back to MVAPICH, as I said right at the front, that I was very impressed that a lot of people didn't know what MVAPICH was because they use it and it works, and the people that did know what it was clearly stated that it was our MPI library of choice. The application base that we got at Pnnl is diverse. In a similar way that we saw Stampede yesterday, I think if I remember the numbers right, 4 billion service units, 2 million jobs. That's a lot of jobs, which means that the job size, even on Stampede, are quite small. We've got modest job sizes too, because of the number of users that we support. But many of those users go on to use the LCFs within the DOE space. I mentioned a little bit about our large-scale systems, and particularly emphasis from where I'm coming from in looking at some of these future systems or potential impact of the technology on future systems. And that's very important in the context of power and reliability as we go forward. And the modeling allows us to explore in advance, as well as plug those into runtime systems and optimize during the execution of those systems. Oh, and I've got a wide range of people that I acknowledge. A wide number of people inside my group here, and also a wide range of different projects that we've got in flight, from the Advanced Scientific Computing Research, OSCA of DOE, some from DARPA, and also from the EMSL, the Environmental Molecular Sciences Lab at Pnnl. With that, I'm going to stop.